Let's look at another example. And this example looks very similar to the previous problem where we have a quadratic function, a quadratic polynomial, multiplied times some other thing. In this case, though, it's not a trig function and it's not an exponential function, but rather a log function. And I've made this just ln of x. This natural log function is not going to be treated in the same way that our trig function was in our previous problem. In our previous problem, we had a same polynomial times a trig function, and we let the polynomial piece be the g. With natural logs, it's going to be a lot better if you let the natural log be your g and let the polynomial be your f prime. Let's take a look and see how that works. Like I said, the natural log throws a wrench into how things are going to work. First off, if I tried to put the natural log in the f prime, we actually haven't seen what the antiderivative of natural log is. We know what the derivative of natural log is. So we're going to put in the natural log into g so that when I take a derivative, the derivative is 1 over x. That is going to force the polynomial to be my f prime. X squared plus 3x plus 1 is my f prime. If I take the antiderivative of that polynomial, I get 1/3 x to the third plus 3/2 x squared plus 1x plus any constant that we want, but we'll use a constant of 0 to make our lives easier. In this scenario, when I'm integrating this, I plug in f times g into my formula. F is this ugly polynomial. G is natural log of x. Minus the integration of f times g prime. Once again, that ugly polynomial, but this time multiplied times the derivative, which is 1 over x. The other second reason that I like to, and that we all like to, use natural log as your g, not only is the derivative something I know, but also this 1 over x can be distributed into any polynomial that we want. In particular, what I can do is take this example or this expression and distribute the 1 over x into the polynomial in here. I'm not integrating yet. I'm just distributing. 1 over x times 1/3 x to the third is 1/3 x to the second. 1 over x times 3/2 x squared is 3/2 multiplied times x to the first. 1 over x multiplied times 1x is just 1. This is an easy polynomial to integrate using our basic rules. What I can therefore do is say that this expression minus the integration of this is my final answer. So let's integrate this polynomial. It's going to be 1/9 x to the third plus 3/4 x squared plus 1x plus c. If you would like to distribute this minus sign, you could do that into all three of those terms in there. We always have to tack on that plus c. And just a note for Moodle, tack it on the outside of parentheses if you ever tack on the plus c. This is how integration by parts works with the natural log. When we have natural log, we let that be our g. Our g prime becomes 1 over x. And then the nice thing happens where 1 over x distributes into another polynomial, and we can integrate that using the basic rules. Let's take a look at one more example of this before I let you do another one. And this example is here to illustrate that the power of the polynomial or the degree of the polynomial doesn't really make this situation more or less complicated. Now that's different from our previous types. In our previous types, the ones where we had polynomial times trig function or polynomial times e to a power, when the degree of this polynomial went up, it became more complicated. Well, in natural logs, the degree of this polynomial can be really, really big. In this case, we have x to the 17th multiplied times natural log of x that we're trying to integrate. However, even though the degree is pretty big, we can do this in one integration by parts step. Let's go ahead and show that. Just like last time, I'm going to set we need a f prime and a g. I'm going to set the g equal to natural log so that I know what g prime is. If I set the f prime at natural log, I wouldn't know the antiderivative of natural log off the top of my head probably. So we set the g be natural log. That way the g prime is 1 over x. That's going to force the f prime to be x to the 17th. If I take an antiderivative of that, I get 1 over 18 x to the 18th power. This integration, therefore, becomes f times g, 1/18 times x to the 18th power, multiplied times natural log of x, minus the integration of f times g prime. F again is 1/18 x to the 18th, multiplied times g prime, which is 1 over x. I'm going to simplify that. 1/18 x to the 18th times 1 over x. Anytime you take 1 over x times x to a power, the power is going to be reduced by 1. This simply requires a basic integration property, namely the integration property of polynomials. Raise the exponent. Did I say integration? Yeah, integration property. Raise the exponent by 1 and then divide by the new exponent. 1 over 18 divided by 18 would cause me to take 18 times 18 in the denominator. That's 1 over 324 times x to the 18th. We always have to tack on a plus c at the end because the derivative of any constant is 0. This is my final answer. 1/18 x to the 18th times natural log of x minus 1 over 324 times x to the 18th plus the constant. That's how we deal with polynomials times natural logs. We let the natural log be natural log of x. It has this really nice derivative that works well with polynomials because when you multiply 1 over x times any term, you reduce the exponent on an x by 1. And that makes something that's fairly easy to integrate. I would like you to try this problem on your own. We have a polynomial times natural log of x, and you're going to use integration by parts to integrate. Push pause on the video, try it on your own, and in the next video, I will show you how it's done.